All right. Hello. Good morning. Hope everybody's doing well. So we are on to our next lesson in our Unit 7, our first unit in Calc BC. And let's recap real quick, and let's make sure we know where we're at standing right now. So we have learned integration by parts. We've learned some additional integration by parts, a tabular method, and stuff like that. We have learned trig IDs. That was the next lesson, which is what this warm-up is on right now. Okay, so you see the kind of setup that we did in our last lesson. So you have some practice with you here. And my goal, as usual, is to hopefully do this with you in person, but we shall see. Right now, I encourage you to pause the video and try these problems on your own. Try a problem like number 1, as well as a problem like number 2. And both of those are using the properties that we learned in our last lesson. Now, number 2 is not a hard problem, just unfortunately it is a long problem. So we have just I divided it up in a few steps. So you're welcome to try that one on your own. I encourage you to pause the video and try it. But for now, let's go ahead and move on to today's stuff. Okie doke. So we're still using trig today, but instead of the lesson being called trig IDs, today's lesson is called trig substitution, because the idea is that we're going to be taking functions that are not trig functions and turning them into trig functions because they'll become integratable that way. Now, obviously, there's certain cases where we can do this, certain situations, and this chart really helps us identify which times to use them. So really keep this chart available. This is your go-to, especially these first 2 columns here. So let's read through this together. You can use trig substitution if you have the following situation. So like if you have a problem that has the square root of a squared minus x squared, where a is just a number, then this identity is equivalent. Okay? Same thing with this square root and this square root. These identities are what we're able to use. So notice the difference between the 3 and the trig ID that we're able to use. So we're introducing a new variable. We're bringing it into a theta, where theta is just numbers between these intervals. And we're going to end up using these trig IDs to help us integrate. But what really helps us are these first 2 columns here. So let me just quickly explain why it is that this square root function is able to turn into this trig function. All it's using is right triangle trig properties to just substitute in some values. So for instance, so for this first one, they're making the assumption that we have a triangle. So we're using the fact that we have a triangle with a theta value. Okay? And for the first one, they're stating that the hypotenuse is x and the opposite side, the hypotenuse is a and the opposite side is x. Well, if that's true, then the missing side would be the square root of a squared minus x squared. Okay, that's just doing Pythagorean identity or Pythagorean theorem. Okay, a squared plus b squared equals c squared. If I'm given this side a and this side x, the missing side would be the square root of a squared minus x squared. So the fact that this is true, the fact that we have this value on the triangle here, with this a value and with this x value, then if I want to bring in a function of theta, well, I know what a and x are. I know that relationship is opposite over hypotenuse, which is sine. So thus, x equals a sine of theta. So using the fact that square root of a squared minus x squared is a value that we have, we can turn that into a triangle problem and use this property. And it's similar arguments for the other 2 as well. Okay, and I encourage you to maybe even try to figure out why those are true and set up your own triangle, but that's essentially what we're doing. So we're turning a non-trig function into a trig function and using trig properties to integrate. So again, they're not terribly difficult, but they're just longer problems. So I got 4 of them today, and I'm going to try to get through as many of the 4 as I can before my 30 minutes are up. And as always, we can recap these, but let's look at a situation here. Okay. Now we still have a list of of other rules to try. I mean, like I would try your basic. I'm just going to label these as your basic integral properties. So you could try that first, or you could try u sub, or you could try integration by parts if you really want to, or the other one we've come up with is trig IDs. You can try those. But these are the two new ones that we learned in this unit. Or you can kind of move on to our new one, which is trig substitution. So the one I always really try is that u sub. The other ones like are particular setup problems. U sub is usually what I try. Like, so if I tried u sub here, u would equal 9 minus x squared, and du would equal negative 2x dx. Now, one of the x's and the dx's substitute out. So I'd have like x du and the square root of u. Okay? But then becomes the issue, like, how do I get rid of this other x? Okay, like, oh, I'm sorry, I had negative 1/2 on the outside. But the point is like, we can substitute in 1x with the x squared and the dx with the du, but I'm still left with 1x. There's no way, and I'm not able to get x by itself here like I would normally and plug in for u. Like, I can't, I don't have that square root, like, I can't take the square root, I can't do it. I can't do u substitution here. I can't plug in something in for x in terms of u to help me out here like I've done in the past. So u substitution is not possible here. Okay? Now, the only thing that's going to end up helping us is that we can identify that a part of this function is the square root of an a squared minus x squared. And in this case, a equals 3. So if you look back to your table, what's the square root of a squared minus x squared? What's that identity? Well, that identity, the ID, let me write it down, is a squared minus x squared. The fact is that x equals a sine of theta. Okay? So this is what we're using from the chart. So if that's true, then x equals 3 sine theta. Okay? So this is kind of the pre-work that I like to do to set this up. I like to identify my a, or really like these two things right here. I like to identify my ID, and then what's trig sub I'm going to end up using. So in this case, it's x equals 3 sine of theta. And just to help me out along the way, I like to go ahead and do dx as well, because I'm going to have to end up doing a dx as well. So dx would end up being 3 cosine of theta d theta. So I like to identify this and then get this. Okay, so if you can do that, you're doing all right. Okay? And now we just substitute out x for theta. Okay, so how it works is we're going to have the integral of. Now, instead of x squared, it is 3 sine of theta squared. So we're going to have 3 sine of theta squared. Okay. Instead of the square root of 9 minus x squared, it's the square root of 3 sine of theta squared instead of x squared. Now, the only other thing, and this is the reason we did dx right here, is because now I want to get rid of dx as well. So I substituted for x, and for dx. Well, dx is the same thing as 3 cosine theta d theta. So don't forget about that. We're going to multiply by 3 cosine theta d theta. Now, the point in doing all this, we used our IDs, we substituted x out for theta. Now, instead of where we couldn't integrate, we just made it to where we can integrate because of our trig IDs. So now, let's just take a second, process that, and see what we can do. All right, now you do this in as many steps as you need to. This is what I like to do. First things first is I like to bring out as much constants as I can. So for instance, notice what we have here. And again, this is 3 cosine theta d theta over 1. On top here, I have 3 squared times 3, which is 3 times 3 times 3. So I can bring a 27 as a constant out. And what I'm left with on the top is sine squared theta, cosine theta, and I'm going to put the d theta right here. And on bottom, what I have is the square root of 9 minus, and I'm going to go ahead and say 9 sine squared, because you can distribute the square. Okay. Now, we took out one constant on top. Now, actually, we can take out another constant out on bottom here. Okay. And what you can do is you can take out a GCF of a 9. Okay. And when I take a GCF, and I'm going to do this over here so I'm not wasting too much space. If I take a GCF of a 9 out, I have the square root of 9 times 1 minus sine squared theta. And I can bring the square root of 9 on the outside of the integral. And the square root of 9 is 3. So what I'm left with when I take out the constant on the bottom is I'm taking a 3 out on bottom. So I got 27 over 3. And I'm left with sine squared theta, cosine theta on top. And on bottom, I'm left with just 1 minus sine squared theta. Okay. So I'm doing this in a couple steps here, but all I did from the setup down to where I'm at now is I just took out the constants on top and the constants on bottom. When I take the constants out on bottom, it's just coming out as a square root. Okay? All right, so now the idea is we're going to end up using some type of trig ID here. That's the whole point of how we set it up. Well, what do you notice? We have 1 minus sine squared underneath the radical. We'll go back to your chart. What ID are we going to end up using? We're going to use Pythagorean ID. 1 minus sine squared is the same thing as cosine squared theta. That's the whole point of setting it up, because we're going to have a trig, like Pythagorean identity, we're going to be able to use. So we're left with, I'm going to write it over here for sake of space, the square root of cosine squared theta, which is equal to cosine of theta, right? The square root of something squared is cosine. So the beauty of this is, I'm going to write this as another step. We have 9 integral sine squared theta cosine theta over cosine theta theta. And the beauty of this and how it's set up is cosines are going to cancel. So simply put, I'm left with 9 integral of sine squared theta d theta. Yay! Okay. All right, now the thing is I mean, we can integrate sine squared theta. We think back to our lesson yesterday and some rules that we need. But remember, we don't like powers of 2 with sine. We can't do trig or U substitution. But there is an identity that we need to know, and that's our power reduction identity. Same thing as 1/2, 1 minus the cosine of 2 theta, d theta. And we should be able to integrate this one okay. So I can bring the 1/2 out. So I got 9/2. Integral of 1 minus cosine 2 theta, d theta. And the integral is not terrible. So I got 9/2 on the outside. The integration of 1 is just, well, in this case, theta, because that's our variable. So 1 is theta. And then minus. Okay, remember, with 2 theta, it's going to come out as a 1/2. Okay, so just go ahead and write that 1/2 on the outside. We're taking care of that 2 theta. And the integral of cosine is sine. So I'm going to put sine of 2 theta. And then plus c. Okay, and I mean, we can go ahead and distribute the 9/2 if you want to. But we got 9/2 theta minus 9 over 4 sine of 2 theta plus c. Okay, now, some of you are saying, okay, good, we're done, yay, thankfully, we integrated, that's fine. But You're going to hate me for this, but once we integrate it, what's the issue here? At the beginning of the problem, we changed it to theta to help us integrate it. But the original problem was in terms of x, so we need to be back in terms of x. You see my issue here? We have theta, we need x. So how do I go back to having x? Well, remember what our original ID was, that x is equal to 3 sine of theta, a sine of theta. That's what we started off with, so that's what we're going to use to go back with. Okay? And if I want to solve for theta by itself, well, that's sine of theta equals x over 3, or theta equals sine inverse of x over 3. So where you see a theta, you're going to plug back in sine inverse of x over 3. So right here is going to be sine inverse of x over 3. So what I have is 9/2 sine inverse of x over 3 minus 9/4. Now, here's another fun issue you run into. This is not my call. This is higher up on me, I promise you that. But we know likey as mathematicians to plug in a sine inverse into a sine function as a final answer. It's a form you will never, ever, ever see as a final answer. You can plug it in over here for theta because you're not plugging into another trig, but you cannot plug a trig back into a trig. Sorry, just can't do it. Well, there's a little bit of a helpful hint to go with this. Okay. All right. Well, first off, the 2 theta, we know likey. In order to do some other trig substitution here, we can't have 2 theta, so we're going to use a double angle formula that's on our chart from yesterday. The sine of 2 theta is the same thing as 2 sine theta cosine theta. Now, this is probably the only time in this course we'll use double angle identity is in this class, is in this lesson, and these types of problems. So I would have that handy. But anyway, that helps get rid of the 2 theta, but the issue is, again, I can't plug in sine inverse into sine and cosine. I can't plug in trig into a trig for my final answer. I just can't. But I do know what sine of theta and cosine of theta are in terms of this problem. I mean, think about it. Sine of theta equals x over 3. Right? Remember how we drew that triangle, right? Opposite is x, hypotenuse is 3, and we have the square root of 9 minus x squared. Okay, I just used my trig ratio here to redraw that triangle. So what is the sine of theta? Well, the sine of theta is opposite over hypotenuse, or x over 3. What is cosine of theta? Well, that's adjacent over hypotenuse, or the square root of 9 minus x squared over 3 plus c. So that's the annoying part, I understand. But we changed it to trig, we integrate with trig, and then we got to change it back to x. Okay, and that's how all 4 of these problems today are going to operate. We're just going to have to think about it a little bit. They're all really similar. I promise you they're all similar to this, but it's just practice makes perfect. Okay? And I guess you could simplify by distributing if you want, but I would leave it that way. That's fine. But everything's back in terms of x. Good. Okay? All right. I'm at 19 minutes. We got 1 problem done. Let's at least try to get 1, maybe 2 more done. I doubt we'll get 2 done, but let's try at least 1 more. All right, example 2. Now you can try u sub all day long, but it's not going to work. Okay, you let u be x squared plus 4. You get 2x. It crosses one of those out. It's just not going to end up being nice. Okay? But what we do recognize is a nice little trig substitution we can plug in. We got the square root of x squared plus 4. So the ID, I guess, that we have is the square root of x squared plus a squared, which if you check on your little chart, the trig substitution that we're going to end up using is x equals a tan of theta. Okay? So where a, I think we can see is 2. So we have that x equals 2 tan of theta. Now, look, you're going to notice when we do this problem, we're doing the same steps as the last problem. So if you want to try this problem on your own, go for it. But remember, we need x and dx. So that's 2 secant squared theta. This is what we need to have to start the problem. That's what we need to have to substitute in. Okay? So it's a little bit ugly, but let's substitute in. You're going to see it simplifies down nicely for us. Okay, so we're going to have the integral of, I'll go ahead and keep that as 1 on top. On bottom, instead of x squared, this is 2 tan theta squared. And instead of x squared again, it's 2 tan theta squared plus 4. So I substituted everywhere I saw an x, I plugged in 2 tan theta. And instead of dx, remember we have 2 secant squared theta d theta. I forgot the d theta right here. So we did trig substitution. Now we're going to integrate this trig, and then we'll plug back in at the end. So remember my steps. I like to start with taking out the constants. So for instance, on top, the constant is only at 2. That's the only constant I see on top. So I have 2 on top. I'm left with just secant squared on top. And on bottom, I have 2 squared that can come out. So that's a 4 that can come out. I also have, okay, 4 tan squared plus 4. I have 4 tan squared plus 4. So just like the last problem, and I typically try to do this without making an extra step, just like the last problem, I could take a GCF of 4 out, so I could take a square root of 4 out of the square root. The square root of 4 is 2, so I have an additional 2 right here. Okay. So then all I'm left with is the tan squared theta square root of, and I got rid of that constant inside the square root. So it's tan squared theta plus 1 now. I took the 4 out as a GCF. I took the square root of 4 out as a 2, and that's what I brought on the outside. So I like to, in one step, bring out all my constants on the top and on the bottom. If you need to do a couple additional steps with that, go for it. Okay? Okay, so now whenever you take all the constants out, especially underneath the square root, the idea is that you're going to see your ID you can plug in. Again, it's another Pythagorean identity. It's always going to be what's underneath, the square root. Well, the square root of tan squared plus 1. So,
teacher, please claim the interruption, but this.
So tan squared plus 1 is the same thing from our Pythagorean identity as secant squared theta. And well, I'll just write this as a separate step. I don't want to lose too many people in this step. So we have 1/4 on the outside. We have secant squared on top. On bottom, we have tangent squared theta. And then the square root of secant squared is just secant theta. Okay, now we need to simplify this, and then we need to integrate it. So just like before, we can cross out a secant and one of the secants. So I'm left with 1/4 integral of secant theta over tan squared theta. Okay? Okay, well, how do I simplify this down to where I can integrate it? Well, I got secant and tangent. Just like when before in our unit back in pre-cal where we had simplified down trig functions, what if I turn these to maybe sine and cosines? So I got 1/4. Secant is the same thing as 1 over cosine. And tangent squared is the same thing as, we can call that sine squared over cosine squared theta, something like that. All right, now, what happens if I simplify that? Well, I think you can simplify this all day long. That's 1 over cosine theta, same change, flip. And then a cosine and the cosine cross out. So I'm left with 1/4 integral of cosine of theta over sine squared theta d theta. Okay, so stop there and see if you can maybe try this on your own if you want to. But the suspense is killing you. Cosine over sine. You can keep trying to simplify trig down, but if I have an integral, this is just a little tip. If I have an integral, both cosine and sine, then you can do u substitution all day long because the derivative of one is the other. Pick u to be what's underneath the square. What if I let u be sine of theta, and du would then be cosine of theta d theta? And here is cosine of theta d theta, so we can do u substitution here at the end. So I got 1/4 the integral of, instead of cosine theta d theta, I have du, and instead of sine squared, I have u squared. And don't you miss the days where we just started off at this line? Okay. All right, so this is the same thing as 1/4 integral of u to the negative second du. And that integrates to 1/4 integral of, or not integral, sorry. I'm going to go ahead and integrate it. I apologize. Integration of u to the negative second. Add 1 and divide, so that would end up making it negative 1/4. And then u to the negative first. And then just plus c. Okay, now plugging u back in, we have negative 1. And I'll go ahead and bring u to the bottom. You can leave it as negative 1 if you want. U we made be sine of theta, so this is negative 1/4 sine of theta plus c. Now don't forget, you're probably getting down to it. You probably see there's no integrals, so you're probably thinking, yay, we're done. But remember, the whole point of turning this into a theta problem is so we can integrate it. We got to take it back to x now. So from this line now down, it's all about changing it back to x. So let's refresh ourselves on how this is going to work. Back to x. So remember what x was equal to. X was equal to a tan of theta, or 2 tan of theta. So theta is going to end up equaling tan inverse of x over 2. But the thing is that there is no just single theta to plug it in for, so I can't plug tan inverse into a sine function. It doesn't work that way. So I'm going to have to use this right here, or I guess the fact that tan of theta equals x over 2. I'm going to have to use that knowledge right here to create a triangle that will help me out here. Okay. So for instance, okay, so remember I got my triangle. This is theta. Remember that with tan is opposite over adjacent, so x over 2. So that would make this part of the triangle x squared plus 4. Or 4 plus x squared, whichever way you want to put it. So then the sine of theta is equal to opposite over hypotenuse. The opposite is x. The hypotenuse is the square root of 4, or I guess x squared, whatever, 4 plus x squared, and then plus c. And honestly, guys, I would leave it that way. I mean, you have 1 divided by a fraction. I mean, I guess you could say this is the same thing as square root of 4 plus x squared over negative 4x if you really want to, but I would probably just leave it as the one above. There you go. It's back to x. And there's no trig in there anymore. There's no theta, and we're done. Okay. Shoot, 2 problems and I'm at 30 minutes, man. Oh well. I guess we'll just stop, and we'll do the last 2 problems in class together later. So, yay, Calc BC! Isn't Calc BC fun? All right, I'll shut up. Y'all have a great day. Great day.